Hello everyone, welcome back to Power Electronics and Laboratory. Today we will learn about discontinuous mode. Actually, the difference between discontinuous mode and continuous mode. And the second point is what is the characteristic of discontinuous mode? What's the voltage transfer ratio? And then third one is what's the boundary between continuous mode and discontinuous mode? What makes the difference between continuous mode and the discontinuous mode? So what changes the state? So those 3 points will be our highlights in this lecture. So what's the definition of discontinuous mode? Discontinuous mode means the inductor current has some zero state. If inductor current has zero state, then we say that the converter operates under discontinuous mode. Discontinuous in Korean means 불연속. 불연속 means having zero value during the on and off state. So during the discontinuous mode, zero current, then diode stops conducting. Diode. So if you look at the slide, when the diode current, the on and off of diode is determined by the current source behavior, right? This inductor is a current source, so it will do whatever it can to maintain the current path. So when we have some value, then this inductor will develop forward bias voltage and diode is turned on and there is a current path. But when the diode current or inductor current becomes zero, then diode is turned off because inductor will not provide the forward bias. Okay, will not provide forward bias for the diode, so it stops conducting. So then, during this state, then capacitor is discharging to supply the current, right? Please take a look at this. If this is off, then whole circuit is disconnected from this. So this only possible source of the load current is this capacitor. So this capacitor discharges to maintain the load current. So this is discontinuous mode. So in conclusion, we have three switching states for discontinuous mode: on state, off state, and diode off state. Okay, so as compared to two switching state of the continuous conduction mode, this continuous conduction mode has one additional switching state. So is it good or bad? It's always exciting to answer this kind of question, good or bad. Okay. Actually, in engineering world, we cannot say good or bad. We have to be very objective. To answer such a kind of question in good or bad means quite subjective, 주관적이죠. So we should avoid saying subjective things. But personally, I like to answer in this manner. Okay. So discontinuous mode is good or bad? In terms of switching state, it's bad. Why? Because it has three switching states, so it's more complex, more complicated to have control analysis, control model. So discontinuous mode in terms of number of switching states is worse than continuous conduction mode. But, okay, maybe it's good that we can summarize here. This continuous mode. Let me briefly explain the advantage, pros and cons, okay, advantages and disadvantages. So discontinuous mode, disadvantage is more complicated control model. Of course, in this lecture, we will not discuss the modeling. Small signal modeling of converter is out of scope, but since we have three states, discontinuous mode is more complicated in terms of control modeling, okay? And then what is the advantage? I'll write in blue color for the advantage. It has smaller switching loss. Loss in switch. Maybe, talking about loss is also out of scope. But just in order to give you some, concept of the loss, I'm now talking about the loss in this switch, okay? In this switch. So, whenever we talk about loss, we have two different kinds of loss: conduction loss and switching loss. And switching loss is generated whenever switch turns on and off. So it's a product of the switch current and voltage. But when the switch turns on, let's take a look at this. When the switch turns on, what's the current value of this inductor here? 0, right? 0. So ideally speaking, there is no turn-on switching loss. Okay, loss is the product of switching voltage and current, right? But in conduction mode, continuous conduction mode, when the switch turns on, there is some current. So current is now commutated from diode to this switch. So there is a certain value of the current. So conduction mode, there is a switching loss. So in terms of the loss, discontinuous mode is superior to continuous conduction mode. Of course, in continuous mode, the disadvantage now becomes advantage of continuous mode. Okay? And what is then the worst or the disadvantage of discontinuous mode is larger peak current in switch. So when we maintain the same load current, since discontinuous mode has 0 state, it should have higher peak to have the same average load. So that's why it requires larger peak current in switch. By the way, student, you don't need to, I'm not expecting you to understand this. I'm just telling you the overview of discontinuous mode and continuous mode. These concepts are not easy to understand, but I'm just expecting you to know that discontinuous mode has certain advantages and disadvantages compared to continuous conduction mode. Okay? And obviously, continuous mode has opposite characteristics. Okay? Opposite. So in conclusion, discontinuous mode sometimes is good and continuous mode is sometimes good. So what should we do? What should we do? The best way is to stay in one mode continuously. Okay? If we change the state back and forth during the operation, that's pretty bad. Okay? So our game of the rule is to maintain the state as unity as possible. So stay in one, mode as much as we can. 그러니까 한 모드에 이렇게 있는 게 좋은 거예요. 왔다 갔다 하는 게 안 좋다는 거죠. 왔다 갔다 하게 되면 제어가 어려워지는 단점이 있기 때문에. So, as I told you in the beginning of this lecture, one of the key highlights of today's lecture is what determines the boundary. Okay? What determines boundary. So, if we know the boundary and if we stay in one mode, then it's pretty good. Okay? So now let's talk about the boundary. Boundary, 경계, boundary. Why are we talking about boundary? Because we want to know what determines the continuous mode and discontinuous mode. 자, 경계 값에 대해서 알아야지만 우리가 어쩔 때 continuous 모드에 있고 어쩔 때 discontinuous 모드에 있는지 아는 거죠. 자, 경계에 대해서 한번 공부해 봅시다. 경계. What is the boundary mode? Okay. Now, let's begin our discussion with inductor current. What is the definition of continuous conduction mode? When inductor current has non-zero value, I said it is continuous conduction mode like this, right? Okay. When inductor current now has some zero value, like this, then it is discontinuous mode, right? What's the boundary then? What's the boundary? Boundary means it's like this. Okay? As soon as it touches the zero, then it's turned on, okay? Like this. So, this kind of waveform is referred to as boundary mode. 경계죠. 그죠? 0이 되자마자 ON이 되면. 0이니까 discontinuous mode 아닙니까? 라고 얘기할 수 있지만, 수학적으로는 경계죠. 하나의 점. So, in this case, now, of course, this is on time, and this is period. And let's refer this as IL peak. And whenever I said B, it means at the boundary. Now, let's calculate this average of this current. This is half of peak value. Okay? Half of peak value. This is average. And everybody knows that this average inductor current is now equal to output current at the boundary, output current. 그죠? 인덕터 전류의 평균값은 출력 전류하고 같다고 제가 누누이 얘기했죠. 왜? 그 리플 성분은 캐파시터로 흘러가니까. The ripple can flow through capacitor and only DC current can flow through load. So now let's pay attention to this IOB. IOB. Okay. This IOB is output average at boundary mode, and this is the half of the inductor peak value at the boundary, and this can be represented in terms of input voltage. Okay, why is this? Because this slope is V input minus V output divided by L. Okay? So slope times the time becomes the current. And if we represent output voltage in terms of input, this output is now equal to duty times V input. So if we rearrange the terms in terms of input, then so this is, what is this? Output current at the boundary. Okay, output current at the boundary. Let's take a look at this waveform as we vary the load. Now, before we do this, let's make certain assumptions. First one is we have input constant this assumption. 자, 가정을 한번 해봅시다. Input voltage is constant and output voltage is constant. We vary the load. It means varying I output. Okay? So, we have two assumptions. Input voltage is maintained to be constant, output voltage is maintained to be constant. Are these realistic? Yes. So my favorite example of charging your battery in handphone. Input voltage is fixed, 220 volt AC, and output voltage is fixed as a battery. Now, every time you charge your battery of your cell phone, then as it charges up to the rated value, then the load current changes. How can it be modeled? Like this, the load resistor is now increased. 그죠? 여러분이 핸드폰을 충전시킬 때 입력 전압과 출력 전압이 결국은 어떻게 돼 있죠? 고정되어 있는 거하고 같은 거죠. 그리고 이제 배터리가 거의 충전이 된다는 것은 뭔가요? 이 저항값이 처음에는 작았다가 점점 커지는 거죠. 커지는 거니까 그건 우리가 어떻게 보는 거죠? 자, I 아웃풋이 V 아웃풋 나누기 RL이죠. 그럼 RL이 점점 커지니까 I 아웃풋이 점점 작아지겠죠. 그죠? Now, under these conditions, now let's take a look. how it determines the continuous conduction mode and discontinuous conduction mode. Okay? Now first, your battery is fully discharged and you want to charge your battery. Okay? Maybe in I don't know, in the restaurant, can you charge your battery in restaurant and convenience store? Huh? And anyway, you pay some money and you charge your battery, okay? So you start with very high load current. So it should be like this. Okay, like I'll use the blue one. Okay. Now, as you start charging your battery, it corresponds to the blue one. Why? Because this has higher load current. Higher load current, like this. Okay. So this condition is called, let's say, 1. Okay. In Greek letter. So, oh, sorry. Let's say this is IO2. Sorry. IO2. Okay. 그죠? 처음에는 로드 커런트가 많이 흘러야 되죠. 저항값이 적으니까 배터리가 지금 많이 방전되어 있으니까. Why do we have same slope? Slope doesn't change. Why? Because the rising slope is V input minus V output divided by L. Since we have a constant input and output, slope doesn't change. And so does the falling slope. Falling slope, how much is it? V output divided by L. I'm always telling you it's important to know about slope. 기울기를 안다는 건 굉장히 중요해요. 전력전자에서 기울기. 인덕터의 기울기는 전압 나누기 전류. 캐패시터 볼티지의 기울기는 전류 나누기 캐패시턴스. 네? Okay? Now, as soon as we slowly charges the battery, now current now is decreased, load current, so it becomes like this. Okay. So this is, oh, my drawing becomes complicated. Okay, 1. So certainly IO2 is larger than IO1. And then as I have explained before, this is IOB, like this. So at some point now we reaches to discontinuous mode, like this. And then, as we continue charging the battery, what happens? What happens? Now the load current should be smaller than IOB. How? That's a very interesting question. 자, IOB보다 작아지려고 하면 어떻게 해야 됩니까? 이거 굉장히 재밌는 문제인데요. 네? 자, 기울기는 안 변하면서 어떻게 하면 요 검은색이 밑으로 확 줄어들면서 이게 요 평균값 전류가 떨어지죠. 자, IOB, 요 I 아웃풋 에버리지는 작아져야 돼요. 왜? 궁극적으로는 0이 됩니다. 그죠? 여러분 충전기 다 충전되면 요즘은 LED가 녹색으로 켜지나요? 그럼 다 충전된 거죠? 그러면 이제 배터리 원래 트리클 모드라고 해서 충전, 방전, 충전, 방전 그렇게 되는데 원래는 전류가 거의 0이 됩니다. 그래서 막판에는 이게 거의 오픈이 돼버려요. 예? 배터리 충전시키는 게. 자, 그럴 경우에는 오픈되면 로드 커런트가 얼마죠? 전류가 없으니까 0이죠. 자, 0이 되려면 어떻게 해야 될까요? 자, 이렇게 될까요? 이렇게? This? Does it make sense? No. Why? 1조. The dotted waveform, does it, I think everybody knows it doesn't make sense. Why? 그렇지. 지금 학생이 슬롭이 일정해야 된다고 얘기했습니다. 1조 맞아? 근데 슬롭이 변했죠. 슬롭이 변한다는 얘기는 우리 가정에 위배되는 거죠. 인풋과 아웃풋. 그러니까 이런 거는 지금 성립이 될 수가 없어요. What then? What could be the solution? Is discontinuous mode. Okay? So we have to maintain the same slope. I'm going to draw the blue one. We maintain the same slope, and then here I have to turn off at earlier time, like this. Okay? So this becomes I-O, let's say B1. I'm sorry. How should I name this? I-O, let's say 3. Okay? Then if I continuously decrease, then it becomes like this. Okay, smaller. Okay. So the only possible way to have lower output current is to have smaller duty ratio. Okay, this is inconsistent with our voltage transfer equations. So, what's the input-output voltage transfer ratio? It was D divided by duty plus delta 1. Okay? Delta 1. What is the definition of delta 1? Delta 1 is 1 minus, Delta 1 is the ratio of off mode during the discontinuous conduction mode. Okay? So, this is fixed in this case. Okay? Under the given assumptions. Okay, so this is fixed. So if this is fixed, okay, but during the continuous mode, this was D. Okay, So as we go into discontinuous conduction mode, if we maintain same duty, then output is increased. So that's why I told you last time the duty should be smaller. 그죠? 제가 저번 시간 막판에 discontinuous conduction 모드로 가면서 듀티가 같은 값을 유지하게 되면 어떻게 된다고 그랬죠? 이 분모가 1보다 작아지니까 커지니까 아웃풋 전압이 커지는 상황이 생긴다고 그랬죠. 그러니까 듀티가 작아져야 된다고 그랬죠. discontinuous conduction 모드로 가게 되면. 자, 봅시다. 여기 작아지죠? 듀티가 뭐죠? 온 되는 시간이죠. 여기까지는 일정하다. 여기서부터 이렇게 작아집니다. 그래서 여러분들이 실제로 그 충전기를 충전시키면서 이제 인덕터 전류 파형을 쭉 지켜보게 되면 사실 이렇게 쭉 줄어들게 돼요. 이렇게. discontinuous conduction 모드로. 네? 자, 그래서 우리가 여기서 알 수 있는 건 뭔가요? 알 수 있는 거는 as the load current decreases, it enters discontinuous mode. Okay? In other words, if I output is smaller than IOB, then discontinuous conduction mode. I think this is the key sentence out of today's lecture. 출력 전류가 경계값에서의 에버리지 전류값보다 작으면 그런 상태라고 한다면 그 컨버터는 항상 불연속 모드, 즉 discontinuous conduction 모드로 동작을 한다는 얘기죠. 네. 그죠? 그래서 우리가 그 강의 초에 얘기했던 경계를 알고 그다음에 어떤 것에 따라 가지고 내가 continuous conduction 모드로 갈지 discontinuous conduction 모드로 갈지를 누가 정하느냐? 이 시점에서는 로드 커런트입니다. 그 로드 커런트가 IOB보다 적으면 우리는 DCM이라고 보고 많으면 CCM이라고 보면 되는 거죠. 네. 그러면 뭐 이제 로드 커런트가 다 0으로 가는 시점이 항상 존재하니까 아까 그 예에서와 같이 배터리 충전 시에 우리가 컨티뉴스 모드하고 디스컨티뉴스 모드로 이제 바뀌는 거는 어떻게 보면 방지할 수는 없지만 예를 들면 나는 항상 디스컨티뉴스 모드에만 있고 싶다. 그러려고 하면 어떻게 해야 되죠? IOB 값이 무지 크면 되겠죠? 네? IOB 값이 무지 크면 된다 이거죠. 그래서 그 컨버터 설계에 있어가지고 이 IOB 값, 아까 제가 지웠지만 그 IOB 값이 설계에 중요한 변수가 돼요. 걔를 내가 키우고 줄이고에 따라 가지고 내가 discontinuous conduction 모드에서 많이 동작을 시킬 건지 continuous에서 많이 할 건지를 결정하게 됩니다. 왜? continuous 모드하고 discontinuous 모드가 서로 다른 장단점이 있기 때문에. 네? 장단점이 있다. 그리고 이러한 사항들은 비단 벅 컨버터만 해당되는 것이 아니고요. 모든 컨버터에 있어서 다 해당이 됩니다. 인버터, 렉티파이어 다 마찬가지예요. 어떤 종류의 컨버터든 다 discontinuous 모드하고 continuous conduction 모드가 있어요. 네. 그죠? So, as I told you before, this black waveform corresponds to the boundary mode. Boundary mode means as soon as it touches the zero, it is again increasing. Okay? So when we have a lower load current than IOB, then now we enter into discontinuous conduction mode. In other words, when the output current is smaller than IOB, then we can say that we operate under discontinuous conduction mode. Okay? So, what is the value of IOB? What's the value of IOB? If I repeat the calculation of IOB once again, it's 2L, we input TS 1 minus D and D, okay? And this becomes 2L F switching frequency, input, and minus D okay. So IOB is proportional to input voltage inversely proportional to inductance and inversely proportional to switching frequency. So here is this, the result. If we want to stay under this continuous conduction mode, okay? Please listen carefully. If we want to stay under this continuous conduction mode, then it's good to have a large value, right? If IOB is large enough, then mostly we can stay under discontinuous conduction mode for most cases of the load. 그죠? IOB 값이 크면 웬만한 로드 커런트에서는 거의 다 우리가 DCM이 되겠죠. 예? 그렇게 한번 돼 보자고 하자는 거예요. 그러면 어떻게 해야 되죠? If we want to increase IOB, then we have to increase input voltage, or we have to decrease inductance, and we have decreased the switching frequency. Then it's more probable to stay in DCM. Okay? 그래서 실제로 스위칭 주파수 값이 작거나 인덕턴스 값이 작아지면 우리가 좀 디스컨티뉴어스 컨덕션 모드로 많이 가요. 실제로. 그리고 인풋 전압을 키우게 돼도 또 디스컨티뉴어스 컨덕션 모드로 가고요. 그래서 이런 것들이 이제 이제 설계 변수가 될 수가 있죠. L이나 이제 FS 같은 경우. Switching frequency. Okay? So now let's solve one example. So, what's the given condition? Input voltage is 2500 volt and output voltage is 650 volt, and the rated load resistance is 0.52 ohm. L is So the question is, is the rated operation fall into CCM or DCM? Okay, so question is pretty simple. Does the rated operation fall into CCM or DCM? Okay, let me explain once again. Here we have a buck converter. Input voltage is 2500 volts. It's pretty high, right? Very large. And this is the realistic spec from electrolysis plant. 자, 전기화학 분해 장치에서 가져온 제가 스펙입니다. 이건 그냥 뜬금없이 나온 숫자가 아니라 실제 산업체에서 쓰고 있는 그 스펙입니다. Input voltage is 2500 volt, output is 650 volt, and the rated resistance is 0.52. Here, the rated current is 1250 amperes. That's the rated. Okay? This one is load output rated. 정격. Okay? And the filter values, L has 570 microhenry and C is 13.5 millifarad. And switching frequency of this switch, okay, is 300 hertz. Now, if I repeat the question again, the question says, does the rated operation fall into CCM or DCM? Okay. In order to calculate this, what's the first step? We have to know about IOB. Okay. We have to know about IOB so that we can tell whether the rated current is above IOB or below IOB. So what is the IOB? If I repeat the formula once again, this is like this. Okay? Input voltage and duty and inductance and switching frequency. So if I plug in these values into this, then 2500. We have to calculate duty. What kind of duty should we apply in order to calculate this? OB, boundary mode. What's the duty under boundary mode? Group 2. How can we determine D? V 인풋분의 V 아웃풋이죠. 자, 바운드리 모드에서 discontinuous 모드에서는 식이 좀 약간 달라지죠. 하지만 우리는 바운드리 모드이기 때문에 continuous conduction 모드 식을 쓸 수가 있죠. 그래서 인풋이 2500V 분의 650V. 그러면 that's equal to 0.26. So now if I plug in this duty value, 1 minus 0.26, 0.26 divided by 2 micro times 300. Okay? This becomes 1406 ampere IOB. What does this mean? When the load current is equal to 1406 amperes, then the converter operates under boundary mode. Now, what is the rated current? This is 1250 amperes, and that is smaller than IOB. So, since rated current is smaller than IOB, we have to operate on the DCM. Okay? We have to operate. So, DCM operation at rated condition. Which means if we operate on the rated condition, now it always operates on the DCM mode. Okay? So, if I give you one more question, then under rated condition, what's the value of duty? Is it smaller than 0.26 or is it larger than 0.26? 자, DCM 전격 조건에서는 듀티가 0.26보다 클까요? 작을까요? 5조. 5조. You have a 50%. Duty is smaller than 0.26 or larger than 0.26? 6조. 질문이 전격 조건에서 동작시키면 듀티가 0.26보다 26은 아니겠지. 그러니까 질문을 하겠고. 왜? 이거는 아까 continuous conduction 모드에서 한다고 그랬으니까. 그러면 이거보다 작아져, 커져? 실제 듀티 값은 커진다고? 작아지죠? 네. 듀티 값이 아까 작아진다고 했지 않습니까? 이렇게 이런 식으로. 네? 실제 똑같은 듀티가 되면 아웃풋 전압이 커진다고 그랬잖아요. 그래서 듀티는 요 0.26보다는 작아요. 제가 이 얘기를 왜 하냐 하면 여러분들이 실수하기가 좋아요. 이게 시험에도 많이 나오는데 discontinuous conduction 모드로 가게 되면 요 식을 쓸 수가 없어요, 여러분. 그죠? 듀티가 작아진다고 제가 얘기했죠. 네. 이거는 여러분들 잊어먹으면 안 됩니다. 네. Okay? So, now, this is kind of one example, okay, right? One example. So, buck converter is pretty simple to calculate. Now, this summarizes our discussion on DC-DC converter, okay? Next lecture, I'm going to show you some animation based on some simulation tool. I'm going to show you some, nice animation of circuit operation. As I told you before, and also in your textbook, there are several different kinds of DC-DC converters. We only learned buck converters. Okay, so what are the remainings? Boost converter, buck boost converter, CHONBUCK converter. And then we have also isolated type of converters. So we have numerous types of converters. So since we have a limited time, we will only study buck converters. But the remaining converters have many things in similars. So which means if you follow the structure of the learning, like we started with topology, operation mode, input-output voltage transfer ratio, and operating mode analysis, discontinuous mode, then you can learn other topologies in a similar manner. Okay? Maybe if I have some time remaining at the end of this semester, I will briefly explain about boost converter. Okay? If I have some time remaining. So next lecture I'm going to show you some animations, and then next lecture now we will start our discussion on rectifiers, diode rectifiers. So diode rectifier is like a workhorse for most power converter solutions. So it's going to be a very interesting topic for most of you. Okay? So if you want to study for buck converters, please read carefully the contents of your textbook, okay? Following my lecture notes. And then at the end of the buck converter contents, there are some different diagrams about discontinuous mode and conduction mode. Okay, there are several different graphs, but please focus on our assumptions. Our assumptions is constant input voltage, constant output voltage. 여러분 그 교재에 주로 제가 여러분 그 오프 캠퍼스 동영상 강좌를 들으신 분들도 아시겠지만 주로 제가 교재 내용하고는 좀 다르게 진도를 나가고 있죠. 그래서 여러분들이 어떻게 보면 좀 교재를 공부하시는 게 힘드실 수도 있지만 또 많은 분들은 또 제 강의대로 따라오시면 좀 더 교재 내용도 쉽게 이해하실 수 있을 거라고 믿습니다. 그런데 한 가지 주의하실 점은 그 DC-DC 컨버터 부분에 끝부분에 가보게 되면 그 discontinuous 모드하고 continuous 모드의 경계에 대해서 나온 부분이 여러 페이지가 있어요. 근데 그 그래프가 좀 약간 그 종류별로 다릅니다. 그게 왜냐하면 가정이 다르기 때문에 그래요. 가정, 즉 무엇을 컨스탄트하게 놓느냐. 그래서 지금 제가 강의 시간에 말씀드렸던 내용은 인풋 전압과 출력 전압을 일정하게 놓을 경우에만 해당되는 거예요. 예? 일정하게. 그리고 로드 커런트가 바뀔 경우. 그럴 경우가 중요하고요. 나머지 경우에는 더 다른 결과가 나올 수 있습니다. 2차 함수 최대값 형식으로 풀었던 게 있죠. 그게 바로 이제 그런 이유에서 한 건데, 그거는 제가 다음 시간에 그 애니메이션으로 여러분 서킷 오퍼레이션 보여드릴 때 조금 더 한 번 더 자세히 말씀을 드리겠습니다. 그래서 교재에 있는 내용하고 제 강의 노트하고 일단 헷갈리지 마시기를 바라겠습니다. Okay, this was average load current at boundary mode, right? At the boundary, 경계. Boundary means what? Between continuous and discontinuous mode. Why we are talking about boundary mode? Because then we know in which mode we are operating, okay? And this was, we input 2L switching frequency duty minus half squared plus quarter. Okay? I think now most of you are familiar with this kind of expression. You learned this in your high school when you are required to compute the maximum value, right? 그죠? 이거 고등학교 때 여러분들 하셨던 거죠? What does it mean? This is like fx, right? Function of x. And what is the x? This one plays a role as x, independent variable, right? Okay? And when you compute for maximum value, then the obvious conditions are these parameters are all fixed, constant value, right? these are not variables. Otherwise, it doesn't make sense. So let's draw this graph. Okay, how does it look like? Usually, we put independent variable in horizontal, but we do it in opposite way. So let's put the independent variable on the vertical axis. So this is gonna be duty, okay? And the horizontal axis is used as IOB, okay? IOB. Then how does it look like? How does it look like? This should be quadratic. 이차함수죠, quadratic. So this should look like this one, right? Okay. So, under which value of D do we have a maximum value? When D is equal to half, then everybody knows that IOB will take the maximum value, right? So this is gonna be 0.5, okay? And this value is maximum, but maximum. How much is maximum? Let's compute the maximum first. IOB max is how much? When duty is equal to half, then this term goes to 0 and we have only 1/4. So it's gonna be 8L FS and V input at when duty is equal to half. Okay? So if we have this term as a like a weight means if we divide IOB by this IOB max like this, in order to have per unit base, then this value is going to be 1. Okay? Now let's take a look at this point. How much is this cross section? When duty is equal to 1, then this whole term becomes 0. So this should be equal to 1. And everybody knows that this intersects the origin at the 0 point. So if I draw more exact manner, it's going like this. 0.0. Okay? So, now, let's take a look at this. I'm going to show you very interesting things. If I talk about I/O, what is I/O? Average of output current. I'm now increasing the average output current, okay? And this means the boundary, okay? This black one means always IOB, boundary, okay? And I'm gonna tweak this diagram a little bit. 자, 제가 요 그래프를 약간 바꿔볼게요. If I switch the vertical variable to V input over V output, okay? Then everybody knows that this duty is equal to V input over V output under continuous conduction mode. So which means if I make this kind of diagram, then when duties when the output when duty is equal to 0.5, okay, then the input output, the ratio becomes same as duty under continuous conduction mode. 자, 이 그래프가 좀 약간 까리한데요. 제가 듀티를 0.5로 유지를 하면, 예? 0.5로 유지를 하면 연속 동작에서는 입출력 관계식이 어떻게 되죠? 입출력 관계식이 연속 동작에서는 이거였죠. 그죠? 연속 동작에서는. 그러면 요 듀티가 0.5니까 요 y-axis 상에서의 V input, V output도 요 포인트에서는 똑같아지겠죠? 같으니까. 그러다가 discontinuous conduction mode로 오면 어떻게 되느냐? What does it mean when we are entering discontinuous conduction mode? If you look up your note, when I/O is smaller than IOB, then we go into what? We go into DCM or CCM? Huh? DCM, right? When we have a light load means low load. 경부하, light load. When we have a light load, then we enter DCM mode. So light load means to this side, okay? This is light load. And this way is heavy load, so-called. Okay? So when we decrease the load, then we have more probability to enter this continuous conduction mode. Then it's gonna be like this. Okay? Why? Why? Because now the duty ratio, input over V output, becomes D divided by D plus delta 1. Okay? Do you remember? If I keep the same duty ratio, then we will obtain higher voltage under this continuous conduction mode. Okay? This is CCM. and this is DCM. So if I use same duty, then we will have higher voltage. Okay? Here. Let's suppose we are moving, we are operating at this point. Okay? Let's take a look. Now I'm applying very heavy load current and I maintain the duty 0.5. Then how much is the ratio between V input and output? Is same, 0.5. Okay? And as I slowly decrease the load current, and at this point now I reach the boundary, and which is still the same, 0.5. And when I cross over this point, entering this continuous conduction mode, while I maintain same duty, then this number is going to be bigger so that I obtain higher output voltage. Okay? And here the main condition is V input is constant. Why? Because this is referred to as a constant value. Okay? 그죠? 제가 요거는 인풋은 요거 인풋 FSL은 상수라고 얘기했기 때문에 요 컨디션이 일단 정해져야 되죠. Okay? And then when I enter into this conduction mode, let's take a look at this. If I apply the light load having duty equal to 0.5, then I have higher output voltage. 그죠? 같은 듀티를 갖고 있으면 discontinuous conduction 모드에서는 어떻게 된다고 그랬죠? 아웃풋이 커진다고 그랬죠. 그러니까 듀티를 줄여야 된다고 그랬죠. 네. So if I draw this same kind of curve for different duty, then this is gonna be like this. Okay? So let's say this is duty 0.25, 0.6, 0.7. Okay? Then this becomes like this. Okay? So the red curve corresponds to when you maintain same duty. Okay? 자, 요거는 same duty에서 여러분들이 출력 전류를 이렇게 줄일 경우에 그때의 아웃풋 전압과 인풋 전압 간의 비를 나타내는 그래프입니다. 근데 X축은 출력 전류를 IOB max로 나눠줘서 이거를 per 유닛으로 표시한 것에 지나지 않는 거죠. This graph is found at your reference textbook. Okay, under the condition of input is constant. You will obtain completely different graph when you assume output is constant. Okay? Why? Because then you will not use this kind of maximum computation. 이게 만약에 output이 constant라고 하면 교재에서 보시다시피 전혀 다른 그래프가 생겨요. 왜? 요 맥시멈을 구하고자 하는 것에 위배가 되니까. 그러니까 여러분들께서는 일단은 요 그래프를 위주로 좀 이해를 하셨으면 합니다. Okay? So the key point is if you reduce the load, reduce the load means increase the load resistance, then you will enter discontinuous conduction mode. And once you enter discontinuous conduction mode, then you will get higher voltage while maintaining same duty. That's the key point. So what should you do when you want to have the same output voltage? Decrease the duty. Okay? You have to decrease the duties in order to get same output voltage. Okay, so now, as I promised at the beginning of this lecture, I'm going to show you some exciting animation. This tool is offered from the university called Swiss Federal Institute of Technology. In German, it's called ETH. It's based on Zurich in Switzerland, and I like to express thanks for the engineers and professors who developed this tool. And I found it very interesting and also convenient to explain to students. And I'm going to show you, I'm going to distribute this. This is anyway freeware. This is freeware, so everybody can use this without any payment. So I'm going to upload and post this tool in our homepage. So both on-campus and off-campus students can freely use this tool. Okay. So now this tool is about the buck converter. Okay. Now I'm going to show you some animations. So what is this? This buck converter. This is a voltage source. You know, European people use this kind of symbol as a voltage source. Okay, this arrow doesn't mean current source. This means the potential drop, plus and minus. Okay. So the people living in different part of the earth are using the different symbols, as always. So, and this is now switch, okay? And this diode. And what is this? Inductor, okay? And this is resistor, this capacitor, okay? This American and English people like to use the coil to represent inductor, but European people, they just shade the color to represent inductor. I think this is more convenient in terms of drawing, right? But this is easily confused. So now you see this green colored dotted line. Now this shows what does it show? It shows the current flowing path. So when I close this switch, what happens to this diode? Diode is reverse biased, so diode is turned off. Okay, so the current flows through this. Okay. What about the capacitor? Is it charging or discharging? Charging. This is like charging. Okay. So this the voltage source is now providing the power to both to the load and to the capacitor. Okay? And to be exact, it also supplies power to the inductor also. And when I open the switch, what happens? Now, obviously this circuit is now floating, and then diode turns on because inductor will force the current to flow through the diode. Okay? Here, it shows that the capacitor is charging, but it's supposed to be discharging. Okay? Here. So, if I use this waveform again, it's exactly the same thing. So what kind of waveform is this? First, what is this one? Can you see in the graph? This is U prime. So this the sky blue color is the input voltage. Now input is fixed. And the blue colored line with little ripple on it represent the output voltage. And the red one is switching function of the switch. So when this is high, then switch is turned on, and when this is off, 0, then it means switch is off. And what is this black one? Switch current, okay? And the sky blue one is diode current. So this and this as a summation represent inductor current, okay? So when switch turns on during this interval, now inductor current as well as switch current is rising with the slope of, how much is slope? V input minus V output divided by L, right? And then here, this mode. Okay? Something is happening here. So when I operate under this mode, then inductor current is increasing. So the load is supplied by the input source. And if I move to the off state, then the diode is now turned on to supply the load current, and inductor current is now decreasing. Okay? Are we operating on the continuous conduction mode and discontinuous conduction mode? From this diagram. Because here we have some mode having the 0 inductor current. Okay? So here, if I go into this mode, then as you can see, the diode is now turned off, and load current is solely supplied by the capacitor discharging current. Okay? So let's take a look at it here, and here. Okay? And as soon as the capacitor is discharging, then you can see the output voltage is decreasing. Okay? Now I have another animation of this. Okay, what is this? Now this graph is exactly the same as I have drawn just before. Okay? This x-axis represent the load current average, and y-axis represent U2 divided by U1. So V output divided by V1, and this is duty. Okay? So you obviously notice that this is similar to what I have drawn just before. And if I move this, what's going to happen now? Now here, this means if I move this red dot to the left side, what's happening is I decrease the load current. Okay? If I decrease the load current, okay, now let's stay in the continuous mode. If I change this, what's happening here? First, input voltage is fixed, of course, because input is assumed to be constant. So that sky blue colored line is kept to be constant here. And what does it do with output voltage? The blue one doesn't change. Why? Because as long as I maintain same duty, output voltage is also same. 그쵸? 아웃풋 전압도 일정하죠, 이거 지금. 이렇게, 이것도. 네? 그러면 변하는 게 뭐냐? The average of the inductor current, right? 평균. Average of this inductor current is equal to the load current. So if I increase this, then this is increased. And if I decrease this, then it's decreased. How does the slope change? Slope is same. 그죠? 기울기는 왜? 인풋과 아웃풋 전압이 같으니까. Now, if I reach the boundary mode, here, now I reach the boundary, and if I move into discontinuous conduction mode, then I have some zero state. And here is boundary, and I move into so-called discontinuous conduction mode. Now, when I go into this, output voltage is increasing, right? Why? Because if I maintain same duty and same input voltage, then output voltage increased under discontinuous conduction mode, right? That's why I told you you have to decrease the duty in order to generate same output voltage. What about the slope? Does the slope change? Yes. 기울기도 변하죠. Why? Because on slope is V input minus V output divided by L, and output voltage is changing, so does the slope. And also the output slope, the falling slope is same as output divided by L, so slope is now increasing. Okay? Okay? Now let's try the other. This is like a toy. Buck converter. Okay. Here you have also same circuit, buck converter, switch. Okay. And diode, voltage source, inductor, capacitor, load. But now you can vary the value. This graphically represent the value. If I enlarge the rectangle, it means I increase the value of inductance. And here does the same thing for the resistance. Okay? And capacitor value. Okay? Now we can play with this. Now this is input voltage, the red one. What is the output? The blue one. Okay? And here I can change also the duty as well as the frequency. It's very nice, huh? Isn't it? So now let's take a look at this capacitance aspect first. What do you see here? First, when I increase this switching frequency, now let's focus on output voltage, the blue one, the ripple. Does it change? Yes. So when I increase the switching frequency, then the ripple becomes smaller. Okay? If you look up your class note and take a look at this ripple factor of output voltage, delta V output, right? That's inversely proportional to switching frequency. So if you increase the switching frequency, now the ripple becomes smaller, as you can see in this graph. What does it look, which one looks better, this one or this one? Of course this, right? This quite has constant output voltage. What's the purpose of this converter? To generate nice flat DC output voltage. That's the main goal of this converter, the main goal of the function. 이 컨버터 역할이 뭡니까? DC 소스에서 DC 출력 빼내자는 거잖아요. 그러니까 리플 없이 리플이 점점 작을수록 좋은 거고 스위칭 주파수가 이렇게 적을수록 스위칭 주파수가 높을수록 우리 이 리플 팩터는 줄어들죠. 오케이? And if you look up the class node once again, and you could see that there is a cutoff frequency. Cutoff frequency is like this. Okay. The ripple factor is proportional to cutoff frequency. So I have to decrease the cutoff frequency. So what is cutoff frequency? Is 2 pi square root LC over 1. So if I increase the capacitance, which means I now decrease the cutoff frequency, so I attenuate more harmonics, then I would get the less ripple. So if I increase the capacitance, then decrease the cutoff frequency, then decrease the ripple. So this is shown here. If I increase the capacitance, then it becomes almost flat. And if I decrease the capacitance, then the ripple becomes large. Okay? Here. So is it good or bad to have large capacitance? Is it good or bad to have large capacitance? Good, right? But the large capacitance, as you can see in this graph, takes more volume and weight and more expensive. So large capacitance is costly for designing the converter. So it's good that we obtain small capacitance and then increase the switching frequency. And what limits the switching frequency? This switching loss. Okay? Okay. Now what about the inductor? Inductor is also the same. Because if I increase the inductor, then I would get the same effect, the low ripples. So if I increase the inductance, then as you can see, the ripple is decreased. Okay. Here. So it's good that we have a large inductance. Okay. So this yellow one now represents inductor current. So now what is this? What am I doing right now? I'm changing the load resistance, which means now I'm changing the load current. Okay? So when I change the load current, what's changing is this. What is this? The yellow one. What does it mean? This is now inductor current. And if I decrease the resistance, now decreased resistance means increasing the load. And increasing the resistance means decreasing the load. Okay, so here, when I change back and forth, the output voltage is maintained to be same. But it only changes the ripple. Okay? Ripple. So, if you look at this, I delta IL peak to peak. I don't know if I use this term. This is also function of duty. Okay? Oops. here, now, if okay. Now let's intentionally go into this continuous conduction mode. I'm throwing many things to you at the same time. This IOB, this boundary mode is proportional to L, right? IOB. Sorry, inversely proportional here. Here, let's take a look at this. So which means if I have smaller inductance, then I have large IOB, which means I have a higher chance of being in discontinuous conduction mode. Here is the explanation. If I have now small l, okay, then if I have a low current, then now we enter the discontinuous conduction mode. Okay? 그러니까 L 값이 작을수록 IOB가 커지니까 우리가 IOB보다 적은 영역으로 갈 확률이 높은 거죠. 예? 그러니까 바로 어떻게 됩니까? 지금 discontinuous conduction 모드로 갔죠. 여기서 인덕턴스를 쭉 키우면 IOB가 작아지니까 바로 continuous conduction 모드로 빠져나오죠. We can do many different kinds of things from the simple circuit, right? That's why the buck converter is so important. I can tell you that once you fully understand buck converter, then you are almost in the halfway of understanding all power electronic circuit. You know, inverter, rectifier, and most of push-pull, half bridge, full bridge, those circuits are based on this buck converter. Okay. Now, once again, if we have higher inductance, then we have a higher chance of staying in continuous conduction mode. Okay. But if we have a low inductance, then as soon as we decrease the load, then we enter discontinuous conduction mode. Okay? I'm going to upload this tool in the homepage so everybody can play with this. So as you can see in the homepage, we have a lot of different kinds of circuit. And also the rectifier and the thyristor and some PWM, many different kinds of things. So I really like this. And also we have a Korean version. Because Professor Choi from CHONBUCK National University also participated in designing this circuit. I appreciate Professor Choi. Okay. 최 교수님한테 제 개인적으로 감사를 드립니다. Okay, so now I'm gonna wrap up my explanation on DC-DC converter. So I'm a little bit. I feel sorry that I don't cover other types of DC-DC converter, but if I have more time remaining at the end of semester, I will come back to this point and talk about boost converter, boost, okay? If I have some time remain, okay? So now from next lecture, now I'm going to explain about the rectifier, diode rectifier, okay? Thank you very much.